Hello, my name is Jamie Tucker-Foltz, and I'll be presenting joint work with Sarah Cannon and Wesley Pigden on sampling balanced spanning forests. This is the 15-minute version of this talk recorded for the STOC 2024 conference. There's also a 1-hour version recorded in an online seminar, and you can find the link to that below this video. Our paper is about the following sampling problem. Given a graph G, such as the grid graph on the left, a k-forest of G is an acyclic subgraph of G containing all vertices and exactly k components. K-forest is balanced if each component has exactly the same number of vertices. So in the example in the middle is a 2-forest that is not balanced, and on the right is a 2-forest that is balanced. The problem is, given a graph G, sample a uniformly random balanced K-forest. Note that throughout this talk, we'll be thinking of K as a small fixed constant. So if you see a runtime of n to the K, I call that polynomial time. So first, note that this problem becomes easy if we drop the balance constraint. Namely, there's algorithms that can very efficiently, at least approximately, sample from unbalanced forests in polynomial time. One way to do this is to take the up-down walk, which is a Markov chain on the space of all k-component forests, and it is known that it rapidly converges to its stationary distribution, which is the uniform distribution on all k-forests. So that's one thing you can do, just run that. However, the forest you get might not be balanced. So a stupid thing you could do if you want to sample uniformly from the set of balanced k-forests is just to reject the ones that are not balanced. And it was recently conjectured that this would work in the special case when G is a grid graph. Namely, a recent conjecture of Charkar, Liu, and Wang in 2022 is that the probability a uniformly random k-forest of a grid graph is balanced is at least 1 over some polynomial function of the number of vertices. And this implies that this rejection step will only tack on another polynomial factor, so this gives you a polynomial time algorithm for sampling balanced k-forests. And so the main contribution of this paper is that we prove this conjecture. We then also extend beyond grid graphs to a wide family of grid-like graphs considering weaker notions of balance, and we also get improved runtimes. So let me first just say a few words about why this problem is interesting. Why balanced forests of grid graphs? And this problem actually arises quite naturally in the study of algorithms for political redistricting, which is the act of partitioning a state up into geographic regions called districts, which will hold separate elections for representatives, say, in the United States Congress. This is often mathematically operationalized as a graph partitioning problem, where the vertices represent indivisible geographic subunits, such as census blocks, precincts, or in this case, counties, and edges represent geographic adjacency. A key task for redistricting algorithms is to output a bunch of samples of random redistricting maps, which are just partitions of the graph into connected subgraphs of equal population. And so one way you can hope to get connected subgraphs of equal population is just to take the graphs induced by a random balanced spanning forest. You need balance for the equal population requirement. And so if you do this, you get some distribution on the space of graph partitions. And this is known as the spanning tree distribution. This is not the uniform distribution on all graph partitions, but that's not really the goal. And actually, there have been both theoretical and empirical work that has been arguing that this is a great distribution to sample from for redistricting purposes. Several algorithms have been put forward to either approximately or exactly sample from this distribution. These are not just academic exercises. They are actually used in high-profile court cases over redistricting and gerrymandering in the United States. However, despite the wide success of these algorithms and the empirical observations that they're very efficient, they have not been shown to be polynomial time. And in fact, before this paper, there was no known way to sample from the spanning tree distribution in polynomial time on any realistic class of graphs. So by showing that random unbalanced forests are often balanced and taking this rejection approach, this establishes actually the first polynomial time algorithms to sample from this distribution on a class of graphs that's meant to reflect the sort of graphs you see in the wild in these redistricting applications. And so while this example you can see is not exactly a grid graph, it shares many properties with grid graphs. So it's a good model that has been well studied for this problem. Okay, so our main theorem is that consider an n by n grid graph where the number of districts k divides the longer dimension m. This is not really an important requirement for divisibility. We could probably get away with k dividing m times n, but this is just much simpler to state this way. So our theorem is that the probability a random k-component spanning forest is balanced is at least 1 over this nasty expression here. And all that matters here is that m and n do not appear in the exponent. This is a polynomial function of m and n because we're treating k as a small constant. So how do we prove this? Well, the first observation is the following lemma, that for any graph, and this holds beyond just grid graphs, for any graph with n vertices, the following two probabilities are related by polynomial factors. First, the probability that a uniformly random k-forest is balanced. That's the thing we want to lower bound. And second, the probability that a uniformly random spanning tree can be split into a k-forest by removing k-1 edges, and that k-forest is balanced. Okay, so it's a slightly different thing. And we're going to focus on the second one because all we need is a polynomial bound, and it's polynomially related to the first one, which is the thing we care about. And that's because it's much easier to analyze random spanning trees. There are many ways to generate random spanning trees, and we just have to pick any one of them and show that it has this property with at least 1 over some polynomial probability. Specifically, the algorithm we're going to use is called Wilson's algorithm. This is a very classic algorithm to sample uniformly random spanning trees. And I've made a little demo here where each one of these squares is going to be a vertex of a grid graph. And what we do is we arbitrarily pick some vertex, which is going to be this white one, to be the root, and then start a random walk from some other vertex, this red one. And we run this random walk until it hits the white vertex. And note that this is not just an ordinary random walk. We're keeping track of where it came from, right? And so this is what's called a loop erased random walk, meaning that whenever the walk runs into itself, it erases the loop and then you resume walking from where you left off. So that guarantees that when you finally hit the white vertex, the walk you have so far is going to be a path, in which case we add that entire path to the tree and then start the random walk at a new vertex. And we keep doing this until all vertices have been added to the tree. And the amazing fact about this algorithm is that no matter where you start the root, no matter where you start every single random walk, you get to make these choices arbitrarily, you will get a uniform sample from the set of all spanning trees. And so we're going to take this to be our process for generating spanning trees. Actually, we're going to do something slightly different. As you can see from this picture, a wide use of Wilson's algorithm, if you Google it online, is generating mazes. And of course, there's another way to generate mazes other than what we just did, which was like sweeping out the corridors randomly. You could draw the walls randomly. And so that's the dual version of Wilson's algorithm, where now we're going to start with a blank canvas and start drawing the walls randomly, still doing the same thing, loop erase random walks. And here what I've done is I've chosen the outer face as the root. So as soon as I hit the boundary, I add that entire path to the tree and then keep going somewhere else. And so this literally is running Wilson's algorithm on the dual graph of the grid. And therefore, it gives me a uniform sample from all dual trees. And there is a bijection between the dual spanning trees and the primal spanning trees. So this gives me also another way of generating random mazes, aka uniformly random spanning trees. And this is what we're going to analyze. So specifically, we're going to lower bound the probability of a bunch of fortunate events happening that is going to guarantee that there is an edge in the primal tree that gives you a balanced split. And so this is just for k equals 2. We're going to give an overview of this proof. And what I'm going to do is I'm going to start the first walk. I'm going to pick some primal edge right here that you can't see. It's invisible. And I'm going to start a random walk in the dual graph right above that edge. And the first fortunate event I'm going to lower bound the probability of is that that walk makes it to the top before it crosses the midline. It doesn't go in the bottom half. Okay, so there, that happened. I just paused the video, and you can see that this made it to the top, and this path never crossed the bottom line. Okay, next we go to the other side of that edge, and we're going to lower bound the probability that that random walk makes it to the bottom without crossing the horizontal midline. Okay, so that goes, and then once that happens, now observe something interesting happens. And that when these two events happen, we know that this primal edge right here is going to be in the tree. And moreover, we know that exactly how to compute whether it's going to be balanced. In this case, it is. We see that there's exactly the same amount of area on the left side, on the right side, just by the symmetry of this shape. So we know that no matter how we fill in the rest of the tree, I can start these random walks wherever I want arbitrarily. I know that this edge is going to be a balanced split edge, meaning if I can remove it and I will get two subtrees of exactly the same number of vertices in the primal graph. So that's basically the whole argument. In a bit more detail, we're running Wilson's algorithm on the dual graph. Here I've drawn the primal graph with these gray vertices and the dual graph, some of these random walks in black vertices. So we pick some edge that we want to lower bound, the probability that this is in the tree and it's a balanced split edge. We start a random walk from A until it leaves this red rectangle and random walk from B until it leaves this blue rectangle. And so the first observation is that with probability at least 1 over n squared, each one of these walks stays within its rectangle until it hits the boundary. And this is a simple application of the gambler's ruin problem, which is just a one-dimensional version. So if you just think about this one-dimensional random walk of just looking at the vertical component, it's starting at like n over 2 plus 1 and has to get to n before it goes to n over 2. And so the probability this happens is 1 over n over 2. So in other words, 1 over n, I'm ignoring constants here. And that means that regardless of what the horizontal walk does, all that can do is leave the rectangle earlier, and that's fine. If it's fine if it leaves here, this proves that with probability at least 1 over n, the random walk will leave the red rectangle either to the top or the sides, never crossing the midline. And similarly for the bottom walk, so we just multiply those together and we get 1 over n squared. Okay, given that that happens, now I need to know what's the probability that this is actually balanced, that these areas are the same. And so like the distribution of areas of like how many vertices x are in the primal graph on the left side versus how many vertices y on the right side, that's some crazy distribution. Probably does not have a nice closed form because of this loop erasure, all this stuff going on. But I know by symmetry that it's the same as the distribution of the difference between w and z below, just because it's the same thing and it's independent. And so I have these two independent events and two independent distributions, the distribution of x minus y and w minus z. And just from the properties that these two distributions are identical and their support size is at most mn, I can conclude that with probability at least 1 over mn, x minus y equals w minus z. Rearranging that means x plus z equals y plus w. In other words, there's the same number of vertices on the left of this whole path and on the right. And that means that I get a balanced split. So just multiplying all those probabilities together, I see that E is a balanced cut edge with probability at least 1 over mn cubed. So that is the bound we get in the special case of k equals 2. For k equals 3, it's quite similar. We just get some worse bounds. Here is the accompanying demo for that. We're going to do the same sort of idea as we pick. Now we're going to pick a couple edges. There's one here, there's one here. And we're going to start these random walks and hope that they don't stray too far left and right and make them all the way to the top and bottom edges before going out of their rectangles. And again, we're just going to have to lower bound the probability that it looks like this and use the same symmetry argument looking at the distribution of areas over on these two sides versus these two sides. This is balanced and similarly this is balanced. And so we get 3 components of exactly equal size with some polynomial probability. As you can see, this gets really bad as k increases. The probability probably is exponential in k, but that's fine for this purposes. We're just looking for the constant k case. The only technical difference in this argument is that now these random walks are not allowed to leave the sides as they were before. And that actually does make things considerably harder. It makes our bounds a lot worse. That you have to get to the very far end of this long and skinny rectangle without going out the sides or the bottom. And the argument we use for that is to first consider the case, okay, so I have some walk that starts here and I want to lower bound the probability that it gets all the way to the top of this skinny rectangle. We first consider the case where the rectangle is square, so it has to leave some constant aspect ratio figure like a square, and then once it does that, that's a 1 over some polynomial probability. But once it does that, now I want to look at this square centered at wherever it first left, at this vertex v1. And I want to say there's a probability at least 1/8 that it's going to leave this square upward and to the left. Okay, why did I choose the left? Because v1 happened to be to the right. And why is it 1/8? It's just symmetry. It's equally likely to leave through this segment, this segment, this segment, this segment, etc., all the way around the square. And so there's a constant probability it goes where I want, and then I've made a constant amount of progress in this rectangle, which has constant aspect ratio. So in fact, going from here, once you've escaped this bottom wall, and you're sufficiently far distance away from this is actually a constant probability that a random walk from here will eventually leave through the top. We'll use this fact shortly in a slightly more general context. Okay, so that's an outline for the proof of general K. I'm not going to go into any more detail than that. I do want to say a few more words about our results for general lattices. And so we're going to think of this as an infinite sequence of graphs where there are infinite graphs embedded in the plane, and they're getting denser and denser. Okay, so as I increase this subscript parameter on the lambdas, these vertices get closer together, and they don't have to have any relationship with each other. This is just the type of objects we're going to consider. And there's a few axioms we need to impose on the graph structure that say like there's not any really long edges or things like that. Read the paper for the details. I'm not going to state it formally. But we imagine taking these infinite graphs and then clipping them to some square region or some other region that we're interested in. And then we're going to ask questions about what's the probability that spanning trees on these graphs have certain properties. And so our big theorem is that if we have a sequence of denser and denser lattice-like graphs, then if I give you any drawing of a partition in the plane. Okay, so it's bounded by Jordan curves. Then as long as I let the density get sufficiently large, for sufficiently large n in this sequence, there is actually constant probability that a random spanning tree of lambda n will be splittable into components that look like the regions in that drawing. So in other words, I take some graph that's sufficiently dense, maybe it's this one, I lay it on top of my drawing, and then I clip it to the outer boundary, and so I don't look at the rest of this infinite graph. Then I take a uniformly random spanning tree, and I want to say there's actually constant probability that a spanning tree will look like this one, where there's going to, so in this case, there were 5 regions, and so there should be 4 edges I can remove, these highlighted pink ones, such that the resulting subtrees are approximately contained within these regions. And so that's our general theorem. This actually happens with constant probability. And what this implies is that we can get approximate balance up to a multiplicative 1 plus or minus epsilon with constant probability. And that's actually the setting of redistricting. You're allowed like 1 to 2% population tolerance, for example, in some settings. And so this is actually a new result, even for grid graphs. This improves because there we got polynomial probability. This implies that grid graph random spanning trees are balanced with 1 over constant probability, not 1 over polynomial probability. I'll just quickly mention that we have one more result that didn't make it into the conference, but is under review currently in subsequent work, that with a few additional assumptions of really technical axioms I don't want to get into, but they're satisfied by pretty much any graph, any lattice of interest, like the triangular lattice, any doubly periodic graph will satisfy all these axioms, even the stronger ones, that we can get additive error with 1 over polynomial probability. So instead of 1 plus or minus epsilon multiplied by the multiplicative balance, it's really just a constant number additive balance in terms of the number of vertices that are difference between the different parts. Okay, so I want to say a few things about the ingredients of this proof. And the first ingredient is a generalization of this argument about getting to the end of a long skinny rectangle, where now we don't just want to go straight upwards, but we actually want to follow some arbitrary curve. And so the theorem is that this, if I take a random walk in one of these lattices respecting these axioms, it should look approximately like this curve. It shouldn't stray very too far from the curve. And the argument is the same exact idea as I presented previously with these sequence of squares, except now we're going to do with circles, where I say, okay, at every step, like say I got to this vertex here, I'm going to look at what is the arc of length 1/8 that this curve exits through, and then I want to say there should be something like 1/8 probability that the random walk in this lattice exits through that arc. And I keep making progress. I keep getting farther along the curve each step, and it's just a bunch of constants multiplied together, one for each circle. Now, of course, we can't say it's actually 1/8 probability in a general lattice. This is the main axiom that we impose on our lattice, is that there is some constant probability that if I start a random walk in this dual graph to the lattice, I will exit any constant size arc with some constant probability. That's the key axiom that these sequence of lattices has to satisfy. So that's ingredient 1. And so that's how you can see that just following these curves is really constant probability this walks will look like this. And there's one more issue that we need to take account of, which is where do you start these walks from? So this is best explained through an example. So I'm gonna go back to grid graphs again, and I want to say there's a constant probability that if I take a grid graph, I will get a partition that looks like this drawing. Okay, and if I take a random spanning tree, there will be 3 edges I can remove that will yield 4 components that look like these squares. And so I'm gonna do the similar approach. I'm going to start a random walk in the very middle of the dual graph and hope that it stays within some small epsilon of the center line and gets all the way to the boundary. Okay, and I've just argued this is like our sequence of circles or sequence of squares argument. Again, it's constant probability will do that. But then when I go to start the next walk, where do I start that from? If I want to start from the center again, do I start like 1 vertex away? It's kind of unclear where to start that walk from, and it's unclear how to prevent it from hitting the previous tree path that I've just added to the tree in my first step of Wilson's algorithm, because remember, if it hits that tree, I have to add that path instead of the path that goes all the way to the top. And so this is actually, it's not true that I'm going to be able to say that the next walk is able to, escape with constant probability. It really is polynomial probability. So how do I get constant probability? And here we're going to do another trick where we're going to use a random walk through the tree to determine the next starting point for Wilson's algorithm's actual random walk. And so it's easiest just to explain this through another demo. Okay, so as promised, we start a random walk in the center of the dual graph. And you may have guessed, this isn't actually like a random sample. I did rig up this algorithm so that it's going this way. But anyway, it's kind of random. Just pretend it's true. Okay, so what happened here? After it reached the wall, we start another random walk, and notice that it like walked through this tree here until it finally left. And so that's the main idea, is I start in the same exact place, and I just keep walking through the tree until I leave. Then I start an actual Wilson's random walk. And if it returns, then I keep walking through the tree again. And the point is that I'm not going to ever be able to say there's a constant probability that any one of these given edges is a split edge in these paths. But if I take the random walk through the tree and the random walk that's actually part of Wilson's algorithm together, this whole process, as long as that stays within this interval, I don't care where it actually separates and breaks free. At some point, I will have a cut edge, and then I will get a partition that looks like what I want it to, with constant probability. So that's the final ingredient to make this constant probability proof work. Okay, so just to conclude, the contribution of this paper was confirming this conjecture of Charkar et al. That random forests of grids are often balanced. In the realm of approximate balance, we're able to get both better probability bounds and extend beyond grid graphs to grid-like graphs. And this all amounts to giving the first proof that we can sample balanced graph partitions from the spanning tree distribution in polynomial time. Thank you for listening.